to this week's Crown Seminar. Our first speaker is Jinhyeun from Georgia Tech University. No, Georgia Tech. Jinhyeun received his bachelor's degree in chemical and biomolecular engineering from Yonsei University in South Korea in 2016, and his master's degrees in energy from Texas A&M University in 2017. Currently, he's pursuing his PhD in chemical and biomolecular department at Georgia Tech, and his research focuses on physics-informed machine learning and the Gaussian process regression. Welcome. You want to try sharing your screen and start the presentation.
Okay. Thank you for the introduction, John Grant. Can you see the slide?
Yes.
Okay, great. Hello, everyone. My name is Jinhyeun Kim, and I'm a PhD candidate in Chemical Engineering Department at Georgia Tech. And my research focuses on the combining different physical constraints into the Gaussian process modeling. I'm really excited, and I really appreciate this valuable opportunity to share my research with the Crunch group. This is the outline of this presentation. I will briefly review the Gaussian process regression and its application in hybrid modeling. Next, I will talk about 3 different methods, which focuses on the hyperparameter optimization process and the informative priming function estimation, and then the development of a new kernel with physics-based knowledge. And then I will briefly talk about the open research directions and conclude this presentation. Gaussian process models, like the other machine learning models, it is good at prediction in training data range, and it has the advantage of the quantifying the uncertainty information. However, it has a not good extrapolation performance, or have a sparse overfitting problems to the sparse training data sets. It leads to the violation of physics laws and lack of interpretability. In this presentation, we focus this part trying to reduce overfitting problems and reduce the violation of underlying physics laws given in the system. It may lead to the improve the generalizability of the model and improve the extrapolation performance as well. In different areas, different fields, there have been active researches to combine data-driven models with physics-based model. For example, the popular one is to entirely replace the first principles model with data-driven model. The other approach is to capture the discrepancy with the observation output and the physics-based output with the data-driven model, or data-driven model can be used to estimate unknown phenomena within a first principles model. The popular one is the physics-informed machine learning, physics-informed neural network, which can be used to solve ODE or PD equation. In industrial engineering field, there is a popular technique called model calibration, which introduced 2 GPs to model low fidelity and high fidelity data with additional calibration parameters. So unlike linear or polynomial regression, which assumes the parametric functional form, Gaussian process regression assumes a correlation or covariance between the outputs. This covariance or kernel is defined by the kernel function. Here, the equation shows the popular Gaussian kernel, and there are some hyperparameters to be estimated, and it contains the tau and WQ in this case. These hyperparameters are estimated by maximizing the likelihood of observing the training outputs. This Gaussian process model assumes the probability distribution over functions, with the assumption that every finite collection of the function output at 2 different inputs follows the multivariate Gaussian. When you have a noise output y and the underlying function f, we can set the prior of the state variable, like the equation 1. It is fully characterized by the mean function m and the kernel function k. Given prior mean, equation 1, we set the joint distribution of observed target values and the function values at the test points, which is given in equation 2. conditioning the joint Gaussian prior distribution on the observations, we can have the posterior predictive distribution, which have a closed form solution, where A is the posterior predicted mean, and B is the covariance information with the posterior hyperparameters. The core of GPR is to use the Bayesian rule to update our prior belief over the function with the given observation data and get the posterior predictive distribution. The popular choice for estimating posterior hyperparameters is to maximize the likelihood function. This GPR is very popular in physics-informed machine learning fields due to its ability that any linear transformation of GP follow GP. For example, if we have a GP for any training output, if we sample from that distribution, then any linear transformation, for example, derivatives or integrals, also follow GP. It has two different schemes as a big picture to embed equality constraints or inequality constraints. For the equality constraints, the main idea is to construct the multivariate Gaussian or joint probability distribution with the observation output and physics-based transform output. For example, if we have the ODE or PDE equation as an equality constraint, we have the GP function, which is the linearly transformed output. We can set the multivariate Gaussian and sample the posterior distribution. For the inequality constraints, the popular one is to use the truncated Gaussian likelihood function to transform the unbounded Gaussian likelihood to the truncated Gaussian. It is popular to embed the bounded constraints for the selected points. Here as well, they select the collocation points, for example, in the pin, and they embed the bounded constraints on that point. It requires the multi-dimensional integral and very computationally expensive, and it may need the Monte Carlo or Hamiltonian Monte Carlo sampling. The challenges of this method is that the sampling of truncated multivariate normal may not be suitable for non-Gaussian or skewed data sets, which is the data is not sampled from the Gaussian distribution data, Gaussian distribution. In this case, the placement of collocation points is extremely important, and it directly affects the performance of GPR. Also, it can generate some intractable posterior distribution for the non-Gaussian likelihood function. In this case, we may use a variation inference to approximate the posterior distribution. For the equality constraints, it may not be practical to construct the covariance matrix that inherently provide different types of constraints. What if we have more than one constraint, for example, equality or inequality constraints? Many of the Gaussian process, constraint Gaussian process regression, targets to embed specific type of constraints, and they may not be flexible to tackle these various scenarios. Moreover, the effectiveness of hybridization in GPR is largely influenced by the selection of kernel, prior mean function, and the method of estimating GPR's hyperparameters. Given the limitations in our comprehension of the complex system, it becomes challenging to appropriately select the suitable configuration because we do not have a full understanding of the system. In this presentation, I will focus on three essential components of GPR: prior mean function and the kernel function, and they fully characterize the Gaussian process regression, and the hyperparameter estimation process in the kernel function. Target system here is when governing dynamics are available with sparse observation data. However, information at hand is incomplete. For example, initial and boundary condition is not given, or they are noisy, and in this case, the non-rigorous settings may result in discovering wrong dynamics of system and non-consonant between initial and boundary conditions, and raise different issues such as singularity and non-convergence. Let's talk about the first method, the hyperparameter estimation. The maximum likelihood estimation is a popular choice by many modelers who use GPR to estimate the hyperparameters of kernel. And it is unbiased estimate for large samples, which means that expected mean is does not far from is the same as the sample mean. So this MLE may however, in sparse data scenarios, it may produce bias estimates. Ill-post means that this estimation process is very sensitive to the perturbation of the small data perturbation, for example, large noise, or cause overfitting problems. This fitted GPR model may overfit to the observation data and can violate the underlying physics of the system. So our question in this paper is, if we have the additional physics-based knowledge as an equality constraint, if we penalize this physics-based knowledge as a violation term during the MLE estimation process, we want to know whether we can find the better hyperparameter set which improve the generalizability of model. In GPR, the modelers in constraint GPR field, they use the property that any linear transformation of GP follows GP. So we reformulate physics-based knowledge as a function of GPR hyperparameters by using this property. Let's say we are given this Burger's equation as an equality constraint. Then we can model this red box with considering the GP mean function, because UT also follows GP, and we have the closed form solution for the GP mean. And this red box should go to 0 for all domain. Ideally, we call it as a physical violation, PV, small PV, at the test point X star. It is important to note that it involves the multiplication between two GP, right? U multiplied with the UX. So it no longer follows Gaussian distribution. However, it does not affect the calculation of the physical violation because we are only considering the GP mean. As pins select the collocation points and calculate the physical violation, we also select the collocation points here using the space filling design. And using the autonomous scale, we quantify the violation of physical constraints and penalize this information during MLE estimation process. This is the objective function. When you look at the yellow box, it is the standard MLE function. It mainly considers the data field, the red box. During the MLE estimation process, we penalize this violation of physics to both consider the data fit and the physics fit of the model. This is the first equation, Laplace equation. We generate a sparse data set from the true solution, which is actually unknown. And by using this governing dynamics and sparse training data set, we want to know whether we can find a better hyperparameter set. There are infinite scenarios to sample those sparse training data sets. So to systematically analyze the effect of physics-based penalization, we define the space filling degree, which is the ratio of the area constructed or convex area constructed with the training data to the area of the entire region. We use around 100 collocation points sampled with space filling design. And this PMLE, penalized MLE function, is a non-convex function. So we need different initializations of the hyperparameters depending on different prior distribution. For example, prior 1, prior 2, prior 3, prior 4. This is the example. First law is the prediction plot of GPR MLE. GPR, where hyperparameters are estimated with MCMC. We assume it is also a data-driven technique because it does not involve significant physics-based knowledge when setting the prior. And the last column is GPR, where hyperparameters are estimated through the penalized MLE function. When you look at the second law, which
Can I
is
ask
the
a question? Can I ask a
Yeah, sure.
question?
Yeah.
Can you enumerate the hyperparameters here? Is it and specifically, how do you compute the covariance kernel? You assume a model with parameters, right? But you didn't show us how.
we use Gaussian kernel for the Gaussian kernel where there's two hyperparameters.
So there's
In
a
this case, yeah.
so there are two. One is the correlation length. The other one is the coefficient in front.
Yes. It is a two-dimensional problem. So we have three hyperparameters. One is the variance of the kernel. The other two is the characteristic length of the kernels in each dimension.
Okay, so it's an isotropic Gaussian kernel.
Yes, I used the stationary Gaussian kernel in this paper.
And in the nonlinear case, you let it be? I mean, you're showing a linear case, but the previous case was nonlinear. So you said that doesn't bother you, but you need to find. I mean, in our paper we had an equation, we derive equations.
Oh yeah.
For the covariance for the kernel.
Yes, right. If it is linear, we have the closed form solution which follows GP. And this is the example. In this paper, we only consider the linear PDE, but for this one, you choose the example for the nonlinear PDE, and because I wanted to show whether we can calculate the physics violation in this case as well, if we only consider the GP predictive mean.
Right. So here, how would you compute the covariance kernel?
We cannot compute the covariance kernel in this case because it does not follow the Gaussian. Yeah.
Fine.
Yeah. Thank you. So when you look at this error plot, the MLE or MCMC method is overfitting to the training data region, the darker region, right? But by penalizing the likelihood function, we can reduce this problem and improve the prediction where training data is not observed. The last row is the prediction for different bounds, and it can also help to improve the prediction of the model. We compute since it is a non-convex function, we need a different initializations. To systematically analyze the effect of physics-based penalizations, we first calculate the standard root mean square error, which is the first law, for different priors and for different sparse training data scenarios from set 1, set 2, and to set 10. Here, gray box or A is GPR with MLE, and the blue or B is GPR with PMLE. When you look at the box plot, it helps to reduce the prediction error in most of the scenarios. For the second law is the mean squared log loss, which involves the uncertainty information. And in general, lower MSLR means the better fit model with a tighter uncertainty confidence interval. In this case as well, we can see that the mean squared log loss can be reduced. This is the schematic illustration of three objective functions. First one is log marginal likelihood function, which is the standard MLE function. In this case, this is plotted as three different hyperparameters, W1, W2, and tau. If we see this image, we can see that we will choose this local optima here. However, this region is actually highly physically violated region. So we penalize this value, this region, and we found the local optima in a different region. And this region is no longer found, eliminated. We calculate the p-values from two-way ANOVA analysis, which quantifies the statistical significance of the two different factors. For example, whether prior impact the SRMSE or MSLL is significant or not. The lower p-value means that it is significant. So when the MLE and PMLE, when you compare between MLE and PMLE function, it is shown that it has a significant impact for both prediction error and mean square log loss in this case. Second case study is a fiber orientation probability distribution model, which is derived from the convection dispersion equation. Here, psi is the fiber orientation distribution, which is a function of position x and the angular displacement phi. U is the fluid velocity, and this p is the dispersion coefficient. This is popular in the headbox system of the paper machine, where fiber is uniformly distributed at the headbox inlet. However, through the contracting geometry, it is aligned to the center line. It is known that it follows the bell-shaped feature of the fiber orientation. This is the prediction plot for 3 different sparse data scenarios. We sample the inlet and the outlet. We sample sparse data at the inlet and the outlet. And this is a fluid flow. This is the best result from 100 initializations for each method. For MCMC, we use the 1000 MCMC draws and with the 100 born in. When you look at the blue plot, which is the PMLE, it captures the underlying dynamics, which is the bell-shaped nature. On the other hand, the data-driven method, it does not capture this underlying nature of the system, the bell-shaped feature. This is the same box plot in this case study too. And when you look at this MSLL black box, it is interesting to see that when we use the MLE objective function, there are 90 outliers above 120. The very high MSLL value, which is not good fitted model. By penalizing the physics-based model, we can reduce or eliminate this region, and this region is no longer found. This is the average SRMSE, mean square log loss, and standard negative log marginal likelihood function value, and the SPV is standardized physical violation value for 3 different hyperparameter estimation methods. So when you look at the SNL ML value, the lower this value is, it means that higher data field. When you compare the GPR PMLE with the GPR MLE, we have a higher value of the SNLML, 0.879, when compared to 0.436. It means that we are sacrificing the data field. When you look at the SPV value, however, we can significantly reduce the violation of physics calculated at collocation points. However, sacrificing the data fit does not necessarily mean the bad model, right? Because in sparse data scenarios, it can actually reduce the overfitting problems. And we saw that the general trend in this research that this penalization can also reduce the uncertainty of prediction. This is maybe because we can reduce the overfitting problems. And this is one of the overfitting scenarios of standard GPR. When you look at the plot, when we observe the overfitting, it is shown that the uncertainty becomes very high in the other region. So reducing the overfitting problems may indicate the reduction of uncertainty as well. We calculate the Pearson correlation coefficient, which calculate the linear correlation between the different vectors. And there is a high correlation between the data fit, SLML, and the uncertainty information. And by penalizing physics-based knowledge, we know that we can reduce the overfitting problems by lowering SLML value which means that we can also reduce the uncertainty as well. There are remaining challenges, however. When you think of the standard GPR posterior mean at test points x prime, x star, this posterior mean can be calculated as a combination of prime mean and the linear combination of a corner at different training points. Here, when you think of an extrapolatory region where test point is very far from the training point, this value becomes very high. And when you think of the exponential form with the negative exponent, this value converges to 0, which means that posterior predicted mean converges to the prime mean. This is the case where in this black box, where this extrapolation region, our model converges to the prime mean. Physical violation amount at test point x prime can be represented as this physics kernel if we have the linear PDE, for example, heat equation. This involves the green box, the combination of corner hyperparameters, because the derivatives of the observation output involve the derivatives of kernel. In this case as well, when test data is very far from training region, this value goes to 0, and the effect of physics-based penalization decreases. This will be similarly applicable for the nonlinear PD as well, because each term will be a multiplication of some of the hyperparameter combination multiplied by the data kernel, K. To tackle this issue, we focus on the prime mean function, which is our second direction. In many GPR modeling, a constant prime mean, the Geoprimium mean is popular choice, and the inference is conducted mainly through kernel. However, when the data are fitted with the stationary GP model, it is observed that the predictor tends to revert to the global mean, which is the blue line here, especially for the region far from the training data points. When you look at this black box, the standard GPR, the prediction of the standard GPR, which is the red line, tends to revert to the prime mean. Conventional approach to tackle this issue is to set the global trend with some of the domain knowledge. For example, instead of set the constant prime mean or Geoprimium mean, we can set the linear prime mean or some of the basis functions, and you introduce some of the basis functions to better estimate the data trend. However, the correct functional form of this basis function is rarely available, and an incorrectly defined trend can worsen the quality of predictions. Current research utilizes the observation data for estimating flexible global trend, but they solely relies on the observation data. But the best fit to the observation data as mean function may not work well when training data does not capture the overall dynamics of the system. However, non-constant global trend is quite common in many engineering systems. Therefore, the choice of the mean function is important and should be carefully selected, but most literature support fails to consider this. This is a motivating example. When you look at the left plot, it is the standard GPR prediction with the Geoprimium mean, purple line. The middle one is the composite GPR, which uses the Gaussian process for the prime mean as well. And the global trend, the purple line, is better estimated, which also improves the prediction of the final model when compared to the red one. We consider the scenario where we have additional physics-based knowledge as a form of ODE or PDE, or in this case, second derivative information. We want to know whether we can utilize this information to construct informative prime mean function so that our final model can discover the true function, as seen in the right plot. We choose pin as a priming function because it is exceptionally good because of its over-parameterized feature of reducing the given objective function, optimizing the given objective function. We first do the GPR prediction with Geoprimium. Here we use the penalized MLE function introduced in the method 1. We can calculate the output F or the F prime or the any term that construct OD or PD formulation. We calculate this value at the selected collocation points and transfer this information to the next step. So here we estimate the priming with pin by minimizing the data fit and the physics fit. Here we utilize it involves the GPR prediction and any of the linearly transformed GPR output that construct the OD or PD given the system. Next, we transfer this information at collocation points to the next step to update the GPR hyperparameters. We iterate this process until criteria is met. Criteria can be the desired reduction of physical violation when compared to the initial violation calculated as autonomous scale at the collocation points. The final model constructs 3 components where A is the priming estimated by pin function, B is the local GPR, and C is the covariance information constructed with this posterior GP hyperparameters. This is the summary of the algorithm. So we do the priming estimation with pin, and given the pin prediction pin parameters, we update the GPR hyperparameters. We run this algorithm iteratively. Let's look at the first Vanderpool equation, which is a nonlinear ODE. We generate the sparse training data points for the given initial conditions, which is in the gray box, and we assume it is unknown. We add 5% uncorrelated Gaussian noise to the sparse training data sets. First, when you look at this black box, which is the standard GPR and PGPR, I want to highlight that the penalization GPR, the dotted line is the 95 confidence interval. It is very interesting to see that this uncertainty interval contains the true dynamics of the system. However, when you look at the standard GPR, uncertainty bound, confidence bound is tighter. The dotted line, the width of the dotted line is tighter. However, it fails to contain the true dynamics of the system. When you look at the second plot, it is the priming estimated with pin and the local GPR. Third plot is PM GPR, which is the addition of the purple line and the yellow line. And it has an analytical expression for the uncertainty information. And final model is the pin, vanilla pin, and it is also very good for discovering true dynamics. This is the physical violation at different training input, different input locations. Physical violation here is calculated as this example in the case of GP. So when you look at the scale of the left plot, which is for the standard GPR and PGPR, and the right plot, which is the PM GPR and PIN, both models, PM GPR and PIN, can significantly reduce the violation in physics. Ideally, it should go to 0 for the noiseless data, noiseless training data. Next, we consider the nonlinear pendulum as an equality constraint. We generate the sparse training data points for the given initial conditions, which is we assume unknown, and add a 5% uncorrelated Gaussian noise. Here as well, priming estimated pin interactively with GPR is very good to capture the discrepancy between the local GPR model and the true dynamics, which result in the blue line, which can successfully capture the true dynamics of the system. Here as well, vanilla pin solely is very good at predicting the true dynamics, discovering the true dynamics. This is a physical violation. And in this case as well, you can see that the PM GPR and pin can reduce the violation of physics. We want to tackle the current challenges that the current methodology of the GPR with inequality conscience. It is very difficult to embed the nonlinear inequality conscience because they use the truncated Gaussian likelihood function. So to make a situation to have the nonlinear inequality conscience, we notice that the total energy within the conservative system is expressed as the combination of the kinetic energy and the potential energy. It is known that when the energy lies within the range between 0 to 2K, the system exhibits periodic oscillating orbits. We set K equals 1 in this system. The true function, the energy value is around 1.99, but we don't know it. We set the nonlinear inequality conscience where the energy is bounded between 1.95 to 2. By embedding this nonlinear inequality conscience, we investigate whether our model can discover the true dynamics of system. Here as well, prime estimated by pin is very flexible and successful to capture the discrepancy of the local GPR and find the true dynamics of the model, which is the blue line. So the inequality bound is plotted as a yellow heighted region. When you look at the scale of the left plot and the right plot, both PM GPR and pin try to reduce the inequality conscience embedded in the model, tries to lie within the yellow highlighted region. As a result, this is a phase diagram which shows the oscillating orbits. Both pin and PM GPR could approximate these oscillating orbits more accurately than the standard or PGPR. Next, we investigate the Burger's equation. We use the initial conditions specified this paper 1, which is the from the Salia, and generate a training data set at 2 test time location at t equals 0.25 and t equals 0.75. Using the governing dynamics with this past training data set, we make a prediction, and the prediction error and uncertainty and physical violation. In this case, for better visualization for the physical violation, we use the absolute value. First, when you look at the black box, both pin and PM GPR can successfully reduce the violation of physics and reduce the overfeeding problems when compared to the standard GPR or GPR with a penalized MLE function. Here we see some interesting observation for the uncertainty. This is the 95 uncertainty interval, the black box right now. Standard GPR, it has a tighter confidence interval, as shown in the left plot. However, it does not contain the true dynamics. By penalizing the physics-based information or embedded the physics-based information through the priming, we can widen this uncertainty interval to correctly capture the underlying dynamics of system. In this case, the hyperparameters in the direction of the time dimension, it converges to the extreme local optima, which means that when you look at the prediction plot, first row of the standard GPR and penalized GPR, we do not see no variation in the time time dimension, right? However, by penalizing the physics, utilizing it as a priming function, we have a moderate values of hyperparameters for the time dimension as well, and we can capture the time variation using the GPR. This is the 1D plot at different time locations. When you look at the black box, which shows the priming purple line, and the yellow, which is the local GPR, it is seen that the uncertainty of the yellow line, the confidence interval, has a moderate interval, right? Uncertainty interval. However, by combining the priming function with the local GPR, it is very interesting to see that the blue curve, the confidence interval for the blue curve, becomes very tight, which means that the uncertainty information also interactively work with the priming function. Here we can also see that the lower negative log marginal likelihood function for the MLE and PMLE, and for the PMGPR, we are sacrificing the data field because we have high value. It may reduce the overfitting problems in this case. The last case study is the Allen-Kahn equation. We solved the discovering dynamics for the given initial and boundary conditions using MATLAB pseudo-spectral numerical method and generate the sparse training data set over domain. Here as well, we show the prediction error, prediction performance, and uncertainty and physical validation amount for 4 different methods. Each column represents the different methods. First, when you look at this black box, penalization can reduce the violation of the physics at the when x and t is high, the upper right corner, right? But it is not enough to correct the behavior of the prediction performance because hyperparameter estimation is actually work under the choice of kernel. It has a limitation. When you look at the PIN and PMGPR, it was interesting to see that this region, by iterating with the GPR and the PIN through the priming function, the prediction error can be improved. And then, which is the maybe generate the future research questions to like utilize different advanced pins to further improve the PMGPR, further improve the priming function and improve the PMGPR function prediction performance. Here I did not represent the uncertainty for the pins because I used the vanilla pin. Next, we can see here as well, PMGPR, the uncertainty bound becomes larger, which means that this confidence interval try to incorporate the true dynamics within that 95 confidence interval. Next, our focus is the kernel function. Because choice of kernel determines the success and failure of the model and determines the dynamics of the GPR process. The kernel in GPR plays a significant role in the performance of model. The plot shows the 4 simple kernels, linear polynomial, periodic, and Gaussian, which shows the covariance values for 2 different input locations. So it is symmetric because they are, it is a symmetric kernel. And when you look at the right plot, which is a prediction plot for using different kernels, even if we use the same observation data set, the dynamics is very different. However, in many engineering systems, the true dynamics of the system may remain obscure. And if only a sparse observation data is accessible, selecting an appropriate kernel for the system becomes a challenging task. Also, many kernels are highly dependent on the observation data structure. Here, the D, the red D, is a distance between the 2 different input locations. Many kernels lie built upon the assumption that if the two input locations fall from each other, the correlation becomes less. This is a very reasonable assumption. However, for the sparse data scenarios, this may lead to the deviation from the insights provided by physics-based knowledge failing to capture the inherent dynamics of the data structure accurately. So our idea is to introduce a new kernel that controls the covariance information on the different physical constraints. Main idea is to penalize the covariance information depending on the physical violation at different input locations. First, as we do in the method 1 and method 2, we first quantify the violation of physical constraints at different input locations given standard GPR prediction. Next, we introduce a physics kernel. We choose an exponential form to maintain the smoothness of the prediction model. Alpha is the newly introduced hyperparameter, which controls the physics fit of the model. So when we have the inequality conscience, y should be less than 0. So this physics violation is just simply the function output, f star. And we try to penalize this information. To consider both data fit and physics fit of the model, we multiply physics kernel with the data fit kernel K. Here, data fit kernel K, we can use different kernel, like the Gaussian kernel, periodic kernel, or more advanced kernel, like advanced, more advanced kernels. There are two hyperparameters, theta, which controls the data fit of the model, alpha, which controls the physics fit of the model. We optimize this theta and alpha iteratively. First, we minimize the violation of physics given the posterior hyperparameters of theta with this new kernel. Next, we maximize the data fit given the alpha we obtained in the previous step. This is the algorithm. So we first formulate the physics-infused kernel depending on different physics-based knowledge, and we iteratively optimize alpha and theta with this new kernel. So this is one of the examples of the iteration plot.
Can I ask a question about the parameterization of the? Can you go back,
sure.
please, in the physics
Yeah.
to show the physics kernel, because it seems that alpha is one parameter.
Yes.
What is new k? In the exponent. Your physics kernel.
Yes, exponent or exponent. It is an exponential.
The exponent. How many parameters do you have there? I'm not sure that you define new k of x minus alpha parenthesis p times new k.
Mm-hmm.
Of x.
This is a PV. PV is the one
V.
vector. Yeah, PV is a one function. So
what is that function?
P is another variable.
Right.
PV is a function. We have one hyperparameter alpha, and PV can be calculated given standard GPR prediction.
So how did you calculate PVK? From where?
Yes, for example, if it is an inequality conscience given in the yellow box, we can just simply set the output of prediction.
No, but I let's say you want to preserve the mass, right? Maintain mass. So for if you have mass conservation as a constraint, how would that physics kernel help you? So let's say you have a conservation law, like mass conservation for species, different species in kinetics, right? Mm-hmm. So how does this kernel help you? Is it sufficiently parameterized so that it can get the physics knowledge?
You mean for the equality constraint? For the mass balance equation?
Yeah, yes, exactly.
Yes, for the equality constraint, I will discuss them later. But
Okay.
equality constraint can be divided by the two inequality constraints. And we found that these two inequality constraints can be combined into one. I will introduce it in the later slide.
Okay,
For
fine.
this one, this is for the inequality constraint.
Okay, thank you.
Thank you. So this iteration plot, the one iteration include the physics violation minimization step and the data fit maximization step. So when you look at the for each iteration, we are sacrificing some of the data fit, but we reduce the constraint violation. And then for the other iteration, we maximize the data fit as well. So under multiple constraints, we introduce additional physics control hyperparameters, alpha 2, alpha 3. For multiple constraints, standardization is very important because depending on the constraint given, if we involve the second derivative information, the epsilon square value becomes very large when compared to the different constraints. One of the requirements for kernel is that it should be positive semi-definite. We know that our kernel is symmetric, so we should meet the equation 1. When you look at the K-physics kernel, it can be represented as the exponential form that we talked before. And actually, it can be divided as a two-column vectors, K star and K star transpose. If we embed this K-physics to the equation 1, we can see that it can be reformulated as a square of the sum function. So it is a non-negative value. So it meets the positive semi-definite condition. It is a positive semi-definite matrix. Since the multiplication of kernels is also kernel, the physics-infused kernel, which is the multiplication of data fit with the physics kernel, multiplication of data kernel with the physics kernel is also positive semi-definite kernel. This is the first example, non-negativity conscience. This is the numerical data. We generate some of the training data, which is the red point. And this is the standard GPR prediction, blue line. And purple line is the GPR with physics-infused kernel. And we can successfully reduce the violation of physics. Y should be non-negative. It is interesting to see that by embedding physics in our method, we can convert the stationary Gaussian kernel, which only depends on the distance between two input data, to the non-stationary kernel, where the input locations are important. We want to emphasize that this method can also correct the behavior for the non-violated region, for example, black box. And we use because kernel works for the entire domain. And if we select the informative priming developed in method 2, introduced in method 2, it may improve finding the true dynamics significantly. However, the example shown in this case studies for the method 3, I only use the priming of 0. This is the PM GPR and the vanilla pin predictions for the non-negativity inequality constraints. They are both very successful in minimizing the inequality constraints. The function value is all larger or equal to 0. But for some reason, they overestimate the function values. Because in general, inequality constraint is less informative than the equality constraints. Also, there are popular methods called truncated Gaussian likelihood function, which is used to embed inequality constraints, and they may not work well for the non-Gaussian data. Here, this is the QQ plot, which shows the deviation of the data distribution. So for example, the blue line is the deviation of the data from the blue straight line indicates the deviation of the data sampling from the Gaussian distribution. So this is the skewed data set. In this case study, the competitive inequality constraint GPR with the truncated Gaussian likelihood, it needs a very careful selection of the collocation points to embed physics, or it may not be solvable. We found another example where the truncated likelihood function works. In this case, the green function, which embeds the non-negativity conscience, it overestimates this region as well. And the uncertainty here does not cover the true function. So this is a summary of the kernel for this example. We first estimate the violation of constraints and embed it into the covariance matrix. And we have the data kernel with the posterior hyperparameters. For example, tau and W in the Gaussian kernel. We multiply these two black boxes and this covariance matrix, which is the physics-infused kernel. We talk about the nonlinear inequality constraints as well, because one of the challenges currently is that it is very challenging to embed nonlinear inequality constraints in GPR. We generate the sparse training data set from the true function, which is a gray box, and change some of the values to set the lower and upper bound of the equation. And we assume it constructs some of the physically valid region, which is the pink shaded region. By embedding these two bounded inequality constraints, we can actively controlling the covariance information as seen in the most right plot to obey the physics we try to embed. We thought that it can be applicable for the equality constraint as well, because equality constraint, it can be divided by two inequality constraints. We can set the physical violation function for two inequality constraints and generate the physics-infused kernel with the two hyperparameters, alpha-1, which controls the first inequality constraint, and alpha-2, which controls the second inequality constraint. Actually, PVK2 is a negative of a PVK1, and they can be combined, which means that we only need to estimate the one hyperparameter, alpha. It is a good news because in general, Gaussian process regression can be computationally very expensive because it is proportional to the cubic to the number of training data sets. Here, alpha is estimated by minimizing the violation of physics for the equality constraints. This is one simple example which is the Riccati equation. And with the sparse training data sets, our kernel covariance information can be corrected, tuned to minimize the discrepancy between the true function and the model prediction. Here we want to try to embed equality and inequality constraints. We assume the reaction, and there is some equilibrium conversion XE of the chemical elements, which have this equation. We assume this is unknown, but the experimenter measures the variation of conversion. We set it as an equality constraint. And from domain knowledge, we assume that this equilibrium conversion is less or equal to 1. We use it as an inequality constraint. This is the prediction plot for when we embed only inequality constraint or equality constraint or both constraints. First, when you look at this one, the orange plot is when we embed this inequality constraint. This actually overemphasizes this region. This is because of we set the priming of 0. When you look at this region and the green box, which we embed the equality constraint, it does not perfectly match. This will be discussed in the later 2 slides. So one of the advantages of this kernel is that it is very flexible to embed different types of constraints and work with different types of database kernels. And this is the ongoing work. And I want to mention that the covariance information operates on the Y space. It is a relationship between the outputs. So, for example, they work on output space. However, physical violation can be in the transform space. So we have 2 different spaces, covariance space and the transform space. We want to interactively transfer the information in each space. When you look at this governing dynamics, when we calculate the physical violation, we can see that even in observation locations for this black box, the physical violation can be high, which means that significant physical inconsistencies can arise at this point, leading to an erroneous penalization of the covariance at those points. This could result in predictions converging towards the priming. We plan to correct this behavior by incorporating physics-based prior routine introduced in method 2. I will briefly talk about the open research directions. So for now, I talked about the priming and the kernel function and the hyperparameters in the kernel. There may be additional possibilities. For example, X is the training input, but maybe we can expand this input space using the physics-based knowledge. The popular method in the similar category is the Bayesian optimization. They start with the sparse data set and they find the new X which they want to sample with some of the objective function, acquisition function, and the popular one is expected improvement. At that selected location, we observe a new output with the offline experiment. We may be utilizing the physics-based information to find the new X location and find the artificial Y instead of doing the offline experiment. For example, Bayesian optimization utilized the acquisition function to choose X and perform offline experiment to add Y. Maybe we can use the physics-based decision to choose X and add Y. For example, we just do the standard GPR and calculate the physics violation. And as an X, as a variable, we can find the physics violation. We can find the new X that maximize the physics violation. Because we want to focus this point first. At that point, we can find the new Y, which minimize physical violation of the model. With the new X n+1 and Y n+1, we can augment our data sets and then do it iteratively until we find the true function. This is the one simple example for the damping equation. Here, I use the uncertainty and the physical violation information to find the new X location. For each selected X, we find new Y, which is the physics-based augmented data by minimizing the physical violation. This may be an open, new interesting work. The final example is that we may use our physics-infused kernel algorithm for the model selection or discrimination. In the chemical engineering, choosing the appropriate reaction law is very important to understand the underlying dynamics of the chemical reaction. There can be many candidate reaction laws from 1, 2, 3 through 4, 5. And the popular scheme, conventional scheme, is that for the given sparse data set between the input variables and reaction rate, which is the output, we do the nonlinear regression to reduce the and calculate the residual scaled error of each model. However, depending on the residual scaled error, the true equation will be 1 or 6. Our reaction rate here, equation predict the observation points with good accuracy. Then our problem is to find the true physical equation. We can utilize physics-infused kernel for the model selection. We can build physics-infused kernel model for each candidate reaction law and calculate the AIC, alkaline information criterion, or Bayesian information criterion, which is a popular criteria for the model selection. In the probabilistic modeling, we choose the lowest AIC, choose the model which produces the lowest AIC and BIC. We found that the true function, the physics-infused kernel, with the true equation, produces the lowest AIC and BIC value, which can discover the true system, true dynamic, true equation for the system. In conclusion, we propose 3 different hybridization methods in GPR with a focus on hyperparameter estimation, informative priming, and the development of a new kernel. This can be physics-based constraints, can either be equality or inequality constraints, and they can be incorporated into GPR modeling. GPR, Gaussian process modeling, have been very popular in the physics-informed machine learning field, and there may be new interesting, there is a very exciting areas that I haven't discovered. For example, we can incorporate uncertainty and better combination of neural network with GPR, with using the deep Gaussian process for the physics-informed machine learning, where we can explore multifidelity outputs or multivariate outputs, or the different problems like the inverse problems, optimization control, or the high dimension problem, using the sparse Gaussian process regression. Also, for the dimensionality reduction or various variable selection problem using lasso or elasticnet, we may embed the physics-based knowledge to improve the selection or consistency of the variable selection. And during my doctoral studies, I was very lucky to be called by 3 different advisors from different departments, and many amazing research fellows from different backgrounds, and the fruitful discussion with them was very helpful to explore different amazing ideas. And thank you for your attention. And yeah, I will happy to answer any questions.
Thank you for the presentation. George, do you have any comments?
Yeah, I have thank you very much for the talk. It was interesting to that you introduced this what you call physics-infused kernel, and it seems to me that's kind of a minimalistic approach to physics, because, for example, we publish a paper where we call it NNGP.
Yeah.
I don't know if you know the paper by Pang and myself, Gofei Pang and myself, on NNGP in Journal of Computational Physics, where we use the data as an input to a neural network, and then you can choose any constraints or any physics that you want, you can put there, and then you get a covariance kernel, which actually follows the physics directly, the data. If the data follows that physics, then so it's more like data-driven than physics driven, but you can combine it, right? Because you do, it's like a pin approach to give you the kernel itself. And now you say why you do that, because of course you want to use GP and you can do the uncertainty, right, and so on. So there's a paper a few years ago, but it's the NNGP, a neural net induced Gaussian process kernel. So the kernel comes directly from that. It depends. I think you show one slide. It will depend on the activation function also that you're using. And then there's another host of kernels that people at Caltech, my collaborators in the MNURI, have developed. Humanohuadi, Owhadi. So he has developed many different kernels, additive kernels also, multiplicative kernels that are like the one that you show, that sort of fits the data or fits the physics. So that, I don't know if you came across that, but he also has a method where he can solve nonlinear PDEs, stationary PDEs, not time dependent like we did in the paper you mentioned, the numerical processes, Gaussian processes. So they can do nonlinear problems using Gaussian process. And he has a theory for convergence for that. So we call that PIN, physics-informed networks, not physics-informed neural networks, so pins with a single end. But that's there's a lot of work that he's been doing, him and his students, and so you may find this useful. Now, your approach is more like a minimalistic one, because and you're right, it's difficult for the constraints, but if you can impose constraints in a pin. But it will be interesting to compare all those three different approaches, yours versus Caltech versus ours, and see, which method is useful where.
Thank you. Thank you for the suggestion. I will do that. Thank you.
Sure.
Any other question from the audience? So I just put the name of the paper I think George just mentioned and the link to the archive version in the chat. So this paper is from the Caltech group, from Humanohuadi and Andrew Stewart. So you may want to check it out. So I discussed with the first author of this paper, and they use the there are two problems, two main problems of applying Gaussian process for nonlinear PDE and data-driven problems. One is the nonlinearity, because GP cannot deal with nonlinearity natively, and one is the scalability of the data. I think you mentioned both in your talk, and I asked the first author of the paper I put in the chat, and he said that I think he did similar stuff in terms of the ideas, not work. So he told me that they use also the mean estimate, not the posterior estimate. So they care about the mean. In that case, I think in the earlier slides of yours, you also, for the progress equation, you also did the same thing, right? You consider the mean instead of the whole posterior. So you may want to check it out. I think this is the paper George mentioned earlier. And I actually have one question regarding the uncertainties. Could you, I think in the first few slides, and when you optimize the hyperparameter for GP, and you obtain uncertainty of the prediction. So I want to ask, maybe it is me who missed it, but what is source of your uncertainty? I think you mentioned using MCMC methods. So is that for sampling the hyperparameters or the posterior distribution?
The uncertainty, right?
Right. Since you assume you only care about the mean of the GP, so what is the source of the uncertainty? Is it uncertain of the hyperparameters of the kernel? Say.
Oh, thank you for the great question. So I think uncertainty comes from many various factors, like the parameter uncertainty or hyperparameter uncertainty. And this one, the uncertainty analytical expression, it mainly tells us the predictive distribution uncertainty. But Yeah.
Yeah, could you go back to I think the first few slides in the method in the second part of the talk where you show the progress equation as the example. No, I think it's earlier in like maybe the third one or the fourth one. No, I mean not example, but in the introduction part.
For the hyperparameter estimation.
For the progress equation, where you show the mean stuff.
Yeah, maybe this.
No, where you define the p by k, I think. Never mind. So you're saying that the uncertainty comes from the predictive distribution, but since you assume that you only consider the physics constraints for the mean of the Gaussian process, so I don't see a predictive distribution from that stuff.
Yeah, so I only consider the mean function of the physical violation.
Right. Because of the nonlinearity, right? The reason why you did that is because of the nonlinearity.
Yes, right.
Okay, so where's the source of uncertainty for that case?
The source of uncertainty, for the hyperparameter estimation penalization, I only use the physics-based penalization for the hyperparameter estimation, and that with that best hyperparameter that we found, I use the standard GPR covariance function to calculate the uncertainty.
Okay.
Yeah, so yeah, we just use the standard GPR algorithm, posterior predictive mean, posterior predictive covariance information, and we just use the different hyperparameters for the first method. So yeah, we didn't investigate the source of uncertainty, for this research, but it will be very interesting. Thank you.
Yeah. Thank you. Is there any question from the audience for our speaker before we move to the second talk? No? Thank you for joining us and presenting your work. It's very interesting work. I think it may take me a few days to fully digest what you present today. Yeah, it's very good work. Yeah. Thank you.
Thank you very much.
Okay, now we move to our second talk. Our second talk is of two parts, about engine problems from Kamal and Varun from Brown University. Kamal is a postdoc in the Crunch group and Varun is a PhD student. And the first part of the talk is about using pinning for engine problem, and second part is using DeepNet for the similar problems. So Kamal, you may want to start.
Thank you again. So this is physics from neural network for predicting gas flow dynamics in diesel engine and unknown parameters. This work is actually collaborated with myself, Suhui Meng, Daniel J. Smith, and Professor George Karnetakis. And we would like to acknowledge the support from Kumar. The paper has updated in the archive, and it is accepted for publication in scientific reports. So this is the content of my talk. So first I'll discuss the diesel engine a little bit, then the diesel engine how it is approximation with neural networks, then physics from neural networks, then problem description, and the physics is from neural network for the particular problem, diesel engine, then numerical studies and summary. So this is a symmetric diagram of the diesel engine. So all our equations actually is we have adopted from this paper. And this is also the figure also adopted from the same journal. So this is a mean value engine model. So here the outside air goes to the compressor. Then from the compressor it goes to the intake manifold, and this is WEGR is easier flow. I'll come to this after going to the cycle. And here in the intake manifold, and it goes to the cylinder. So in the cylinder, it's the fuel is added. This is the fuel, and then it goes to the exit manifold. From exit manifold, it's again recirculated back. So that's the easier and the easier flow. And then it goes to the turbine, and turbine, this is the goes to the outside of the engine. And this is where the turbine speed is there. Then it's rotate the compressor. So it has 8 stages. So 2 stages for intake pressure and exhaust pressure. Then these 2 are the exhaust gas ratio. Then this is omega turbine speed. Then this is for UGR, and this is for VGT. And the inputs are, this is the easier control valve, and this is VGT control. Then this is fueling, and there's one more engine speed. So this is a first order model. So it's a first order model with the stage, then the input and the engine speed. Out of this, in this present study, we have considered only 6 of them, because these 2 are not dependent upon the other stage. So we have not considered that too. Okay, so let's discuss one by one how these models are there. So first, this manifold pressure, intake and exhaust manifold pressure. So these 2 models are based on the ideal gas law and the conservation of mass. So in the intake manifold, these 2 are the coming from compressor and easier, and this is going to the cylinder. So this is going to cylinder, and this is similar to like the PV is equal to nRT in the differential form. And for the exhaust also, from the cylinder, this is the exhaust manifold flow, and these 2 are the output to the environment and the easier flow. So out of this TEM is a time dependent variable, and these are also time dependent, but other part is constant. So TEM is modeled using this equation. So this is the heat transfer coefficient of the exhaust pipe. So there are n pipes, and this is the diameter of pipes, and this is the length of the pipe. And this is T. This is okay. So the nomenclature are all T are temperature and P are pressure. W is the flow. And then this is TEM. It's a temperature at different point in the engine, and this is a no ideal gas constant actually. So here okay. So there are other equations. I'm not keeping those other equations. There are 2 variable XR and T1. So XR is the ratio of the gas, and T1 is the temperature at some points. But these 2 equations are cyclic. You can see here. So these 2 depends upon one another. So what we have done, we have approximated these 2 states and these 2 equations using 3 neural networks. And we consider these 2 parameters as unknown. The total gas transfer coefficient and compensation for non-ideal gas. Why you consider this? So if anything changes in the value of the H2 from the design value or eta SC, we can infer the health of the engine. So if it changes, so it's indicated that the exhaust manifold has some issues, so we can have some maintenance requirement. Then comes to the cylinder. Cylinder, there is no differential equation. These are all algebraic equations. So it's coming from the air is pushed from the intake to the cylinder. So this is what is coming to the cylinder. This is the fuel added. So this is fuel added. So this is the fuel added. So it's given by this equation. And this is the going for intake, and this is outside going to the exhaust manifold. Okay, so there is an empirical formula, this eta Coulomb, which gives the efficiency of the cylinder, volumetric efficiency of the cylinder. So in the present study, what we did, we considered that to as a neural network instead of doing a regression model. And how it is trained? So this P means it's pre-trained. So it's trained using level data and level data are calculated from this. And these are actually, this can be done using laboratory tests. It's not need to be in the field. Then comes to the exhaust easier valve. So easier valve has 2 parts. One is a easier valve actuator. So this is given by this equation. And why this type of equation? So there is a So easier value 0 means completely closed, 100 is the complete open, and it's model as delay and overshoot. Delay overshoot means if my easier input is something like this, so I have a delay and it goes overshoot and come back. So that's why it's model using two equations, not one equation. And we approximated these two states using one network. The second part of easier is the easier flow. That's the W easier flow, which comes from the intake manifold through the easier valve to goes to the, exhaust manifold to the intake manifold through the easier valve. Okay, there is two parts. One is the pressure ratio. Okay, this pressure ratio controls that there is no backflow from intake to exhaust. And the second part is this effective area. So this effective area is actually a function of the easier actuator. So these are linked here. From here, this is the easier, and that goes links to controls the flow of the gas from the exhaust to intake. And there is an empirical formula again, which is given by this equation. So we consider that this is as an unknown for the pin problem. So why it is unknown, we consider. So if any problem is there, easier, say some deposits are there, so it will change from the design value. So we can see that, okay, there is some maintenance requirement in the easier, and we can have a maintenance in the easier. And then there is the network, which approximate this easier. And this is trained using the laboratory test from easier. There is a catch here. So this is the pressure ratio, and if we go here, this can have a 0. So something like we avoid the 0 with a small number. Then goes to the VGT. VGT is have one equation, so there is no overshoot. So this is something like, if this is the input and there is a delay, and that goes to here. So the easier has a overshoot something like this, but VGT doesn't have a overshoot. And this is the turbo speed. It's given by some differential equation. This is based on Newton's second law. And there is one empirical formula, which is the turbine efficiency. And then there is some additional equation. I'm just skipping one equation. And we approximated this part using one for the engine speed, turbine speed, another for the VGT, and this eta Tm is here. And how does eta Tm is calculated? So this is calculated using this formula. Okay, so here is again, this part is difficult to measure in the lab even. So what we did, we used this equation. And then yes, this is a differential equation, so we can't solve that. Then we approximated using a fifth order approximation, and PC can be calculated. So we calculated this part from here, and then since it's a differential equation, we required a very fine delta T and dynamic data. Next is VGT flow. VGT flow is given by this equation. So there is also two parts. So one is this pressure ratio, which give the pressure between the atmospheric and the exhaust manifold. So this controls that there is no backflow from outside to the VGT. And then there is a parameter which related to the VGT actuator. So there's two empirical formula which control this. One is related to the pressure ratio, and the second was related to the VGT. So we combine, we consider this as to be unknown, because if anything is problem is there, so the VGT value will change from the design value. And instead of considering these two different equation, I combine them to be one equation here, and then approximated with one neural network, which is pre-trained. Then this level data can be calculated using back from this equation here again. Next is the compressor flow. Compressor flow here, and then this is the one empirical formula, which gives using this actually. And there is another one which give the compressor power. There is a compressor efficiency. This is the efficiency of the compressor. So generally what is done, this compressor efficiency is calculated from the design chart. There is different chart which give the compressor efficiency, but for the present study, we consider as an empirical formula. It's actually similar design chart only, but it's using a numerical, they consider empirical formula, and we approximated these two using two networks, one for the psi, one for the efficiency. Instead of using a design chart, we use a neural network. And then these are the level data calculations for the eta C and phi C. Now goes to the pin part. Now this is a standard pin from here. This part is a standard pin where the time is the input. Then this differentiations are taken using automatic differentiation and then updated. For the present study, we have
Kamal,
yes.
can you summarize a statement of the problem? What is the data that is given? What we're looking for? How many neural networks has you have assigned and so on? But what I miss is a comprehensive problem statement.
Oh, it is there afterwards actually. I summarize them.
Okay.
Okay. So there is this P-chain network. So this is the simplest version of actual problem actually. So P-chain network, the output goes to a P-chain network and then comes here. So this is the unknown parameter, and then there are some weight for the loss function. We use self-adaptive weight for this. Yeah. So the problem statement. So problem statement, we have two objectives. One for predicting Azure, eta SC, and H total. We have data from the field, this 4 data, PIM, PM, omega T, and WZR. And the second part, we have 4 unknowns with same data input. And then we have data, 2 types of data. One is the field data for the pin part. One is the laboratory data for the P-chain networks. And the operation range of the machine is from -40°C to +40. And then the pressure is from 0.7 Pascal. It's at height of 3000 meter. And then from 1.1, which is at the 17.9 meter. So pin can take automatically the operation range, but for the P-chain network, we have to train with the P-chain network with the entire operational range. So this is the data generation. So we have some data, real data for the inputs, but we don't have the output data. So we just use some simulate model, which available in along with the same paper. They have published this link, Simulink, and we obtain the output. Since the inputs are real data, we assume that there is inherent noise, but for the output there is no noise. So we added the noise based on 3%, 3%, 1%, and 10%. Why they are different? They are used, this data are in field uses different type of sensor to measure. So that they have different noise level. This WZR is highest one because WZR is not calculated directly. It's calculated from pressure measurement across the EZR. So it has more error. So for the training and testing data, we have for the pin part, we are using this at this temperature, this temperature and the pressure. For the P-chain network, we are using the entire range from -40 to +40 and different pressure elevations. And we have a 2 hours data, actual field data for the inputs, and then 20 minutes for the testing part. Yeah, so this is the where we have summarized. So we have 6 P-chain networks, which calculated the empirical formula. One for this is for cylinder, this is from EZR, this is for VGT, this is for turbine, this is for the compressor, this is for the compressor. So these 6 P-chain networks is for the empirical formula. Then we have 6 networks which estimated the states plus these 2 cyclic variables. They are not tested, but they require because of the cyclic nature. And the 4 unknowns. AZR max, there's a maximum effective area of the EZR file. So if any changes from that value, we know that there is some issue of the EZR. We have a maintenance issue. H total is for a non-ideal cycle. So we could give whether the engine is running on anything is a non-ideal cycle. And then H total give the transfer coefficient in the exhaust pipe. So if my exhaust pipe is not working properly, so my H total will change. And this is the VGT maximum area. So if anything, any deposits are there in the VGT, the value will change. Okay, so this is the flow chart of the problem. We have 6 networks. This is actually similar to what we have shown this one. So it is just for our present problem, this is combining all these networks. So we have 6 neural networks which are here. Then one is here, under here. Then 6 preteens, one here, 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 and then four unknown quantities. These 2 are in the cylinder and the exhaust. This is for the EGR, and this is for the VGT. I will not go through its calculation wise, but the details are in the paper, and they calculated the residual loss because using this. So whatever we discussed, this is the complete scenario of the flow chart. So we have 6 pretend network, 6 networks. So this is important. Why this is important? So I discussed that there should not be a backflow of gas. So this should, the equations are only valid only for positive quantity. So these 2 functions using soft plus and sigmoid, we maintain that there is no negative quantity and there is no backflow from the any of the component. And this scaling is required because we saw that they are on different scaling. So we use a normalized scaling to normalize all the different quantities one scale. Then these are the pretend networks. These are very simple, like using data-driven modeling is trained. Using these are the inputs, each networks, and these are the 6 quantity for the empirical formula. Next, the loss function. We have used self-adaptive weights, and without self-adaptive weights, we have pin losses. So these are the 6 pin or 8 pin losses. Then we have this initial condition loss, and we have some 4 data. For these are the 4 data quantities. And then this lambdas are the self-adaptive weights, and gamma what we have. So I have shown here. These are the unknown quantity. We have 6 networks, so 6 weights and biases. Then I use Adam and LGFGS optimizer. Here the self-adaptive weights are not optimized complete in the Adam optimizer. It's only optimized up to some point where some sufficient accuracies are there. Then after that, it's only optimize the network parameter and the unknown. And for without self-adaptive weights, this is the loss. I remove the self-adaptive, and these are the standard constant weights instead of self-adaptive weights. Next, numerical results. I studied 4 cases. So for 2, 3 unknown and 4 unknown, then we have noise clear data for each cases and noisy data. And this case 5 is without the self-adaptive. Then there is a mask function considered for the unknowns. So why this mask function is required? Again, the same logic. This should not be a negative. So this will make sure there is no negative quantity. And then since we can see here, they have a -4 and this is -4. So these are the scaling so that it converts faster. So this is results. The 4 unknown with self-adaptive and without self-adaptive. Case 5 is without
Kamal, can you explain a little bit of the scaling factors? Because, for example, in systems biology, we may also need to, what is the scale, mask and scale consider? Can you just explain this a little in detail for the people who are having similar problems?
Okay. So this 4 quantity is physical quantity. Okay, so they cannot have a negative value. So this exponential function and soft plus function, it will make sure that there is no negative. And if it is negative, there will be a backflow of gas from any of the system. So it can be any other function, exponential or absolute value also is fine, but it should be a positive value. That's what the mask is there. And if we see the numbers here, this is 10 to the power -4, and this is 10 to the power -4, and this is in terms of 100. So I make sure that they are in the similar scale. So this is the scaling I use. So in the optimizer, it only calculate actually the 4, not the exponent part. Anyone has any query on this?
The scales match because 1 is 10 to the -4. Why do you multiply by 10 then?
Oh, okay. Because if we see the actual number, the design value is in 10 to the -4. So to make it the actual optimizer quantity is 1.
Okay.
So that all the 4 quantities in the same system, like the actual optimized quantity is in the same numbering, and all the exponents are outside the optimization part.
Okay, keep going.
So this is 4 unknown case with the clear data. So we can see they are almost matching with both with self-adaptive, without self-adaptive both. There is a mismatch with T1 and the XR. So we study how much this affects these two. So these two variables are coming in these two quantities. So we see that there is not much effect given they are very highly deviated from the actual one. And here we can see actually the effect of self-adaptive weights. So case 3 is with self-adaptive, case 5 is without self-adaptive. So self-adaptive weights are giving better results. And these are the weights after training, the self-adaptive weights. To have a more reliable check whether how much self-adaptive weights are accurate from the without self-adaptive weights. So I ran the test for 30 times. And you can see here actually the blue dots are with self-adaptive and the red dots are without self-adaptive. So they are all are poor than the with self-adaptive. And this is for the noisy case. So we are using simulated data in the output. So I use noise. So we can see here they are matching except this one. Some small point, one or 2 points, they are not matching. Then goes to this is the convergence, how it converges if even with noisy case. So Azure, ETS, to tell and AVCT max. Then we have some empirical formula. So this is the predicted empirical formula. This is with noisy data. So we can see even with noisy data, we have very good except this part, but the effect is not that high because other part is almost matching. So in the summary, we propose the PIN method for the estimation of prediction of dynamics of engine and parameter given some few of the measured value. The input is considered from actual running condition. This is one of the difficulty because actual running condition will have a noise. So that we have to control the noise and very fast dynamics. For that we use self-adaptive weights because of the very fast dynamics, and it shows a very good convergence. And we don't have any temperature measurement. It's because it is very difficult, so we didn't consider for the present study, and thus we expect some errors in the temperature measurement and the unknown quantities because we didn't consider any temperature measurement. Approximation of empirical formula, different quantities used. This is better than using a least square method, because least square method we need to approximate. We need to assume the nonlinearity whether they are square type or cubical type. But using neural network, we need to assume the nonlinearity. If sufficient data are there, it will learn the nonlinearity between input and output. Future study. So this is going. Hopefully, this will be installed in some car or somewhere. So it required more robust spin method so that it can be run in a edge device. And since there is a lot of noisy data, so uncertainty quantification is required. Few other study may possible, like the failure of the easier. If easier is failed, so the actual physical model has to change, but the present physical model doesn't have any leakage in the easier or any of the component. So that may be one of the future study is possible where there is a leakage or there is a failure in the sensor itself. So the data are completely wrong. So some neural network method is required where there is a failure. And then any advanced method of pin which is very fast for and can be run in a small computer device, so edge devices. And thank you for this is from my side. Any query, question, and discussion is there?
Thank you, Kamal.
Yeah.
Any question from the audience about pins for this type of problems? If not, we'll move to the second part where deep nets are employed for similar problems.
Hi, Kumar. This is Healy. Actually,
Yeah.
very good work. Actually, I have a question for the. You have designed a very complicated model for this. So can you talk a little bit about the insight behind this? Why do you use 6 network for the parameters, right? 6 network for the state variable, if I understand it correct.
Yeah, not 6, 8. Sorry, 1, 2, 3, 4, 6 networks. So here is this is what you are asking, correct?
Yeah, yeah. So this for the model parameters, right? So they are like time dependent. So that's why you use a neural network instead of equation. Is that
No.
correct?
So those are here. This one.
Okay, so those are the state variable of the ODE or the parameters.
No. State variables are these. These are the state variables.
Oh, okay. So there are six neural network for the
6
state
neural net,
variable.
yes. Yes.
So why do you split it? Why do you just use one neural network for that?
Okay. So if you see the results, they are completely different. So these two are similar. That's why we combine these two. Then
Okay.
easier are similar. So easier is combined. Then PGT is completely different. And then omega is different. So that's why they are different. If we so that's why PM, these two are similar. So this is one neural network. These two are similar. So we put these two one networks.
Okay. You split it based on the dynamical behavior.
Based on the dynamics, exactly. Yeah.
Okay. And for the
second
variables.
Second part is like if we put one network, this network size may be very high. I didn't check, but it may be very high. So it may not be suitable for small computer like the edge device. If we put one network.
Okay, but if you split it, does it impact the interactions of those variables? Because those variables are actually coupled, right? They're computed from coupled ODE.
Yes, they are coupled ODE, but they are interrelated based on this flow chart. So they are already related actually.
Okay. And for the unknown parameters, you basically assign each neural network for the unknown parameters.
No, unknown parameters are constant, so they are like trainable variables.
Oh, okay. That considered constant.
They are not trainable variables.
Okay, got it. Thank you very much.
Yeah, thank you.
Any other questions? Okay, thank you, Kamal, for the presentation. We'll move to our second part. So, Varun, are you ready?
Yeah, 1 second.
Sure.
Okay, is my screen visible?
Yes.
Okay, so yeah, thanks, Kamal. So this part of the talk, I'll be discussing about how we use like a deep net to predict like the output gas flow states. We are dealing with the same problem setup in terms of like the data and all. The only difference here is that we are using a deep net to predict the output states. And this work is again in collaboration with Somdata, Daniel, and Professor Kanedakis. So this is the overview of my presentation. So I'll briefly go over the research motivation, why we wanted to build a DeepNet model. And I'll talk briefly about the 1D gas flow model. Kamal already talked about it, but I'll just touch briefly on what we're trying to do with a DeepNet. I'll discuss the DeepNet architecture that we have used. And then I'll go over the methodology for data generation, training the network, how we estimate the uncertainty and robustness of the models. And then I'll go over some of the results and discussions, some limitations that we found with the DeepNet model, and summary, and then ongoing future work. So one of the key requirements for this project, especially from our sponsor, is that they need a model which is able to predict in real time and also be accurate. And this is very important for like real systems like a combustion engine, because it's the transient behavior is very fast, and the output response that you're trying to estimate from a model has to be accurate as well as real time. So that was one of the key requirements. So there are analytical models available which are based on physics, but it's difficult to model the complex nature of such systems using physics alone. So there's like a requirement to add physics and data-driven model while trying to model complex behavior of combustion engines. People have used machine learning based tools and they have shown good results. One of the challenges with using machine learning methods is that sometimes the generalization can be poor, because these systems operate at different environmental conditions, different ambient conditions. So sometimes your model cannot generalize well. And also uncertainty of these models has not been clearly established when you deal with like real systems. So the research goal for this work was to establish a framework which can combine operator-based model with physics, and then use that for identifying parameters from a system of ODEs in real time. So what we are trying to do is we are trying to develop like a DeepNet operator model, and then we want to link it to like physics-based equations and try to estimate the parameters, which is what Kamal did. And the objective for using a DeepNet instead of just pins is that pins can take time because you have to do like automatic differentiation, which needs like you have to traverse through the whole network. So we want to minimize that part so that we can actually increase the efficiency of the computation. So I'll just touch briefly on the mean gas flow model that we had. So this is a schematic which was adapted from this work from Wallström and Ericsson. So these are like researchers from Sweden. So basically, like in the schematic, the things that you see in the green, like ellipses, these are the inputs, like the speed of the engine, the fueling, and the position of the two valves. And the outputs that we want to estimate using a DeepNet operator are shown in the red squares. So these are like things that like we have the pressure in the exhaust manifold and we have the pressure in the intake manifold. So there are actual sensors on the engine which can actually measure these two pressure values. Then there is also a measurement for the turbo speed sensor. So we have these measurements. We also have like estimates of like the actuator signal for the two actuator signals, and XR and T1 are basically states of the cylinder that we want to estimate. So basically the problem is to use the four inputs, which is the fueling, the engine speed, the UGT, VGT, and the EGR valve positions, and try to predict the output states, which is given by the pressure values in the manifolds, the speed of the turbine, and the states XRT1 and the actuator signals. So that is what we are trying to do. We are just trying to map like the inputs to the output states that I show in this diagram. To give like the audience an idea of the type of data we are working with. So like I'm showing the data that we have. So the input data that I show on the left side is basically showing the engine speed. So this is data that is collected from a test bed. When an engine is actually running, there are sensors to collect the engine speed data. So this is the type of data we get from like our sponsors. And then we use this data, and we actually use this data as an input to our model, the 1D Simulink model that we have. And we actually generate the output states. So the data is very chaotic, and there is no pattern or there is no defined trend. But this is just like it's simply because that's how like an engine operates. You can change speed and you can change different engine operating conditions, and the data appears like to be chaotic. So the DeepNet architecture that we use consists of like 7 different trunks. We are trying to estimate 7 output states: the pressure in the manifolds, PIM, PM. XR and T1 are the states for the combustion of the cylinder. Omega T is the speed of the turbo shaft. And UEGR hat and UVGT hat are the two. So basically, this is the actuator signal from the EGR and the VGT valves. And for the input, we are using engine speed, the fueling, how much fuel we like supply into the cylinder. And we are using the EGR position and the VGT position as inputs. And then we actually use a total of 9 branches, and we separate like, you see like a separation between like these 2 states. You see like the network being separated like between the output state, like the output for the EGR actuator signals and the 5 signals that I show here. And that's mainly because these actuator signals don't really depend on engine speed and fueling. They're mostly dependent on, like if you look at the equation, they're dependent on the EGR and the VGT position alone. And that's why basically these can be considered like as a separate DeepNet by themselves. We have a total of 5 branches for the 5 outputs that I show here. And we have like the time is actually going into the trunk. So we have like 5 trunks for one for each output. And the time input actually goes into the trunk network. We also have like some initial conditions which are used as an input. And this is something that we found that because the data is so chaotic, we had to use some values from the output, use that as like initial condition inputs to our branch to like improve the prediction accuracy. So we are using only the data that is measurable, which means it is available to us in the field. And we use like the first like point, which I'll talk about this later as well, but we are just using like one data point as an input to our branch to help us with like reducing the error in the prediction. So the training process is shown in the schematic that I have here. So we have input data which comes from the field in the form of speed, fueling, EGR position, and VGT position. Then we use the Simulink model, which is like what Kamal talked about, to generate the output states. So these output states are basically the ground truths that we use to train the model. And then we use the same input in a DeepNet model to like basically generate the predictions. And then we use like the ground truth and the predictions to train our DeepNet model. Important thing to note here is that the output from like the Simulink model is noise free. So we don't have any noise in the output when we're using like a simulated data. In terms of data preparation, we had to do some like, we had to rearrange the data. And this was basically found heuristically that if we arrange the data in the format of like having like a number of samples times window size, like I show in this diagram, that helps improve the training of the network. And this is something that we determined like based on trial and error. So we had to arrange the data in like a matrix format, like I show you. And we also had a certain set of data. So we partitioned that data into training and testing set. So for testing, we are actually selecting like a section, 1000 second long section from the data, while we are using the remaining data for training. And then we also normalize the outputs and inputs with the max and min values in the data set. And this is basically to get like the scale for all the data, to basically change the scale on to 0 to 1 for all the different data, because like each data has a different scale in this case. And about the initial condition, so like in the signal that in this data arrangement that I show, the initial condition is basically we pick 1 point from each row, and that is what we use as the input in the branch, the initial condition branch that we had shown earlier. And this we found was required because otherwise it was very difficult to capture the behavior of the outputs. We did some more work where we actually removed the use of this initial condition, and we tried to chain like the output from like the first signal, use the end last point as an input to as an initial condition to the next signal. And I'll show some like results for that as well. So we did like both used initial condition from the data as well as use predicted output as an initial condition in a sequence to sequence type learning. So this table shows the architecture of the DeepNet. So we have like the branch layers have a depth of 3, and they have like 128 neurons each. The hidden layers are using switch activation function, and the final layers, some of them use ReLU, some of them use sigmoid, some of them are linear. So this is basically based on the type of outputs we need. So some of the outputs, like Kamal also talked about, they need to be positive. So that's why we use like ReLU. Some of my outputs actually needed negative values as well. So I had to use like a linear activation function there. We also use dropouts because initial testing showed us that this whole system, the data we have, tends to overfit. And in order to avoid that, we had to use dropouts. These dropouts actually give us another feature, which is we can use this to understand the uncertainty, epistemic uncertainty of the model as well. So it basically serves like two purposes. One is reduce the overfitting and also help us understand the uncertainty in the model. We also use self-adaptive weights because we wanted to capture the sharp transitions. And we use like the GPU, NVIDIA A40 GPU, and the training took roughly 3 hours. So some of the results we found, so this figure I show is the result for like the noise-free condition where we don't have any noise. We see like good prediction for all the 7 states. And the actuator predictions are very accurate or more accurate than the others because these two mappings were easier to make. The input and the output mapping was easier to actually predict, whereas the other 5 states have more complex relationships. But overall, the prediction looks good. Here I'm only showing the first, I'm only showing the 60-second time window because otherwise, it's very hard to see what's happening. But in the next slide, I'll actually show you. Here I'm.
Varun, this slide, it is 10 second and combined again, correct?
What do you mean by that? Sorry.
In the previous slide, you have shown it is 0 to 10 second, then it's like 10 second is predicted and combined.
No, so we can predict like all 1000 second at once because that's how the data is arranged. So you don't have to do like 10 second at one time. You can just predict 1000 second like in one shot.
Okay.
But I'm only showing the first 60 seconds because otherwise it's hard to see the results. In this slide, I'm actually showing the prediction results for all 1000 seconds. Image on the left is the first 500 seconds, and image on the right is the next 500 seconds. So overall, we see good predictions. There are some areas where like you have sharp peaks where we are not able to capture those. But apart from that, overall, if you look at the predictions, the quality of the prediction is good. So the next thing we wanted to understand is like, how does the noise, if we have a model that we train with the data we have, and we send it out in the field, what happens if the input data has noise? So in order to simulate that, we basically added Gaussian noise of different levels to our inputs, and use the same model that was trained on noise-free data to see what is like the change in the output. And the table here shows like as you increase the level of your noise, the error also increases, but the increase is not like catastrophic. So it's not like it's just starting to predict. The errors don't like change significantly. There is increase in the error, but it's not like it's not catastrophic as such. And the maximum value of the error, 3%, this was basically based on the type of sensor that I use and the expected noise that we are probably expecting to see in the field. So the next thing we wanted to understand, or like wanted to test, was because initially we used like the output values as initial conditions. Now we wanted to see if we can actually use the prediction of the DeepNet and use that predicted value as an initial condition to the next set of predictions. And this is important because in the field, the output data that we have, it may be corrupted or it may not be accessible due to various reasons. You have a corrupted sensor, and that means your output measurement is faulty. So we want to see if like the model can actually, if we can use like sequence to sequence chaining type of setup to actually still come up with predictions for the output states. What happens if we do this is basically it leads to error accumulation, because the output for each signal that we have, there is an error there. And if we keep adding that to the next set of predictions, the error builds up. So the figure on the right that I show is basically showing the line in the blue shows the initial conditions when we use data as an initial condition. And the red dotted line shows you how the error increases as we use like sequence to sequence initial condition chaining. So mostly it's like in the pressure and the two pressure and the turbine speed, that where we see maximum error buildup. The actual model is actually pretty accurate, and I think this is also because the error doesn't build up so much here, because I think the model is able to capture the different. It's easier to capture the input and output mapping in this case. So you don't see the same level of error buildup with the actual signals. And this table shows you the comparison between like when you have the initial condition from the ground truth, the error that we had, and once we have sequence to sequence chaining of the initial condition, the amount of error we see. So we do see like higher error, like up to 12% for the output space PEM. But I mean, that's something that we can work on, and we can try to improve that as well. So we also had like, one of the objectives was to understand how uncertain this model is. And to understand the epistemic uncertainty of the model, we actually use dropouts that we already had in the branch networks. And because dropouts are like fast and cheap, that's the reason why we wanted to see, we wanted to use them to see how uncertain the model is. So what we did, we basically generated like an ensemble of like 100 test predictions by enabling the dropouts. And then we basically use the mean of those 100 predictions to determine how uncertain the model is. So what you see is like, even with like an ensemble prediction, the error is still relatively similar to what we had with like the deterministic prediction. And even like the maximum error that you could expect to see was like around 12.6%. So this is like at the boundary of the 2 sigma. This is at the 2 sigma boundary, the 12.6% error that you might expect to see. Also, because the dropout values were like small in the actuator models, that is where we see the maximum increase in the error when we use an ensemble type of prediction. So it basically shows that dropouts have like a good effect on the network in terms of reducing the impact of noise, as well as reducing like the uncertainty that you might expect to see in your model. Some of the limitations. So the results I shared earlier, when we look closely at some of the other time sections and we actually zoom in to those sections, so that error is not uniform. So like earlier we showed like errors in the range of 5 to 6%. But when you look at some of the other sections in details, the error are actually higher. Like in this case, the PEM error is higher, up to 16.7%. Some of that is attributed to the fact that like some of these scenarios, like a flat line, which is basically showing an engine idling condition, those are very hard to capture because like they are not represented well in the training data. So some of these things and some of these sharp like peaks that you see, sometimes it's hard to capture because the training data does not have enough representation for these type of events. So that's like one of the limitations. And the other limitation is if you have to extend this to like other engines, the parameters that was used in the original Simulink model needs to be estimated again. That's one of the other challenges that we have if we want to extend this to like any engine in the field today. So in summary, in this work, we like present an operator network which is capable of effectively learning the operator mapping for the engine control stimulus to the desired gas flow dynamics. You observe like a maximal to relative L2 error of 6% or a 1,000 second prediction window for the baseline model. And this is probably like acceptable for someone who is trying to use this for an initial development work. We see good accuracy with simulated noise addition to inputs and outputs. Although I did not show the results for outputs, we actually tested noise addition to the outputs as well. And the model performs, the results are accurate. And it's not like, it's not predicting trash at that point. We also test sequential chaining of initial condition, which is like a practical alternative if you don't have the output measurements or if the output measurements are corrupted. We do see higher error for this, and that is like another area of improvement that we can work on. And we have used dropouts as a cheap alternative for uncertainty assessment, and also as like a regularizers to for our network. And the limitation that we have is the model is not equally accurate in all sections of the data, so the accuracy is varying in different sections. Ongoing work. So the original goal or the objective was to actually create a pre-trained DeepNet and try to integrate that with like a physics-based model. So this is what we are working on currently, where we have this pre-trained DeepNet, and the last layer of the DeepNet we are actually using for transfer learning, and we are trying to add basically physics-based equations to learn the last layer. And in the process of like training this last layer, we are also trying to identify the unknown parameters that Kamal talked about. So what this lets us do is, because the trunk is that time input goes into the trunk, and we are only learning this like this last layer, the gradient like or while solving the like ODE equations that we have for the physics, the gradient with respect to time, it does not have to back propagate through like this whole DeepNet. We can actually pre-compute this the gradient with respect to time of the trunk and simply multiply with the output of the branch, and then basically try to learn the physics and extract the parameters. So that is very significant for us because calculating the gradient with respect to time actually is a time-consuming process. And if you can pre-compute the gradient with respect to time outside the training loop, that helps us actually achieve like very high computational efficiency. And that is like a very important requirement for this project, that we need to be able to predict the parameters in real time or like in minimum time. So that's an ongoing work. We have like initial results with that, but that's like work in progress at the moment. Yeah, so that's the end of my talk, and thank you for your attention, and I'll be happy to take any questions you have.
Thank you, Varun, for the presentation. Any questions from the audience?
Hi, this is Jerome Dabon from Brown. I wanted to have an idea when you have this huge peak that are hard to predict.
Yeah.
Is it because we inject a lot of fuel? So essentially, the engine is idling, then you accelerate, or you try to accelerate a lot? Or what is the scenario?
It's generally when your speed shoots up, that's when you start to see those high peaks, because as soon as you like press your accelerator pedal, you have to inject a lot of fuel, and basically all your dynamics in your actuator have to change at the same time. And that's one of the reasons why you see those high peaks like all of a sudden in the data.
Do we see that also when we slow down? When we have to brake a lot, maybe?
It will like generally when you brake, you are like going from like a steady state condition to like a noisy condition. So you will actually see some of the pressure values. I don't know exactly how it will look, but I think it will like tend to go down and then start to like show peaks in like lower peaks. It will not be high peaks, but it will be like peaks at a lower level.
Yeah.
And one of the most challenging conditions to model is actually the idling case, because when you're idling, a lot of things are not optimized in terms of the engine calibration. So you'll see a lot of like high frequency noise when you're trying to like model the idling case. And those are the situations which are very difficult to capture with like neural networks.
Yeah. I see. Thank you very much.
Yeah.
Any other question? Comments from the audience? All right. Since there's no question, thank you, Varun, for your presentation. And it comes to an end. And thank you, Kamal, for your previous presentation on PIN as well. So it comes to an end to this week's Cron seminar. Everyone has a good weekend. See you next week. Bye.